Right, we're going to go through, cover a bit of the reading that was in physics classroom on mechanical energy, and I'm going to talk a little bit about conservation of energy as a whole idea. That'll be really quick. So let's just get right to it. So when we talk about conservation of energy, and if I ask a lot of students, what do they know about conservation of energy, they will say to me that energy can neither be created nor destroyed, only changed or transformed. What does that mean in regular words? So in regular words, that means that the total amount of energy never changes. It only transforms into different types of energy, like potential or kinetic or heat or sound or lots of other types of energies that they're out there. Nuclear energy, electrical energy, chemical energy. There's plenty of them. But let's go through a quick example that might seem a little bit confusing, like maybe we're destroying energy, but we're really not. So let's talk about a baseball player. So a baseball player slides along a level path into second base. So he goes from moving, and he's got a certain amount of kinetic energy. So let's say he's got 1,000 joules of kinetic energy. As long as he's sliding along a level ground, he really has no change in potential energy, so I would just say his potential energy is zero. So what happens at the end of the slide? Well, now he's going to be stopped. He's slid into second base, he's safe. So where did that kinetic energy go? If he's no longer moving, well, now he's got 0 joules of kinetic energy. So what happened to this 1,000 joules? Did we destroy it? No, we did not destroy it. It was transformed into heat and sound. Sometimes you get those raspberries when you're sliding if you're a baseball player, and there's friction involved. So that transforms into heat and sound. And there's going to be exactly 1,000 joules of that to bring the baseball player to stop. The total amount of energy has not changed. It's transformed from kinetic energy into heat and sound. The tricky part with heat and sound is it's really hard to quantify it with numbers like formulas or anything like that. So a lot of times we'll deal with systems that we kind of ignore friction and sound and any of those kinds of losses. And when we do that, we tend to focus on this idea of total mechanical energy. And it's abbreviated TME, or just ME for mechanical energy. And it's the sum of the potential and the kinetic energies. No other energies are considered. We just look at those guys. And we kind of pretend that our system is isolated and that doesn't change. And on the physics classroom, it talked about this mechanical energy as giving us the ability to do work, like cranes lifting things, if we look at how potential and kinetic energy can transform into each other. So let's talk a little bit about conservation of this mechanical energy. Again, simplest cases that we're going to deal with. If we don't consider any friction, then total mechanical energy is conserved. And that means the same thing. It means that this total amount never changes. If I add these two numbers together, it's always going to be equal to the total energy, and that value won't ever change. So as we apply that, if we lift something up, so let's pretend we throw a ball up into the air. And we know from previous units of study, as something is thrown up in the air, it's going to start to lose its speed until it gets to the top and it comes back down again. We remember it loses speed at a rate of 10 meters per second every second. We kind of learned that with throwing things up in the air. So we're now applying this to energy. So if the potential energy goes up as it goes higher, it's going to slow down. That means that the kinetic energy is going to decrease. How much is it going to decrease by? It's going to be equal to the same amount that this increases by, so that if I add these two together, I still get the same number. And that's the idea that we want to kind of look at for this. So I want to go over to a quick sim just to demonstrate that. And this is in my pendulum lab. So a pendulum is just swings back and forth like a playground swing or anything like that. So here's my pendulum, and notice over here we're going to represent the amount of energy that this pendulum has using bar graphs, and I'm sure you've seen bar graphs before. So we're going to have a kinetic energy bar graph that's going to give us an indication of how much kinetic energy the pendulum bob has, then the potential energy. This red one is the thermal or heat, and that's putting friction in. We're not going to do that. So you can see over here we have no friction in here. And then this E total is kind of representing the total mechanical energy of our system. So watch this, and this is important because we're going to do this later with a lab sim that we're going to be involved with. If I take this pendulum and I lift it, right, I'm applying a force to lift the pendulum up. Notice what's happening with the bar graphs. Okay, as I lift it up and hold it there, my potential energy is increasing. So the work that I do, lifting the pendulum back, is going to be the potential energy. And notice at the same time, the total energy is exactly equal to that potential energy, which is exactly equal to the amount of work that I've done to lift the pendulum bob back. And again, this is going to be important when we start looking at roller coasters and the ski racer example that you saw in the physics classroom. So now I'm just going to let it go. And I have this in slow speed. So if I did normal speed, it would swing really fast, but it's kind of hard to see that really when it's going so fast. So I'm just going to put it in slow speed. So as this thing swings through, notice kinetic goes up, potential goes down, potential goes down, kinetic goes up. But the total amount, which is the sum of the green and the blue, the kinetic and the potential, that's staying rock solid. This is conservation of mechanical energy. And now I'm going to pause it right at the bottom if I can kind of get it right there. So I'm just kind of pausing it. It's swinging through. I'm like taking a snapshot here. All that potential energy has gone to zero. So this is what we mean by a zero reference line. This is the lowest point that this pendulum is ever going to go. So when we measure the height, we measure relative to this lowest possible point. So no potential energy. All of the energy is kinetic. And if we remember, kinetic energy goes as the square of the speed. This is where the pendulum is going the fastest. It's when it's at its lowest possible point. Now I'm just going to let it keep going. And then I'm going to try to pause it right there at the top of the swing. So think about being on a playground swing. This is where your speed goes to zero for that moment. You get that little butterflies in your stomach because you're kind of at that highest point. You kind of feel a little weightless. And this is where it's turning around. I have all of my potential energy, no kinetic energy, but my total energy stays the same. And again, as we kind of swing through, and maybe we get about halfway down there. I did it pretty close to being halfway. Half kinetic, half potential, total amount stays the same. So that's the big idea with conservation of mechanical energy. So whether we're talking about a pendulum or going down a great roller coaster or a ski run, it's the same idea. The total mechanical energy of the system stays constant. It merely shifts from potential to kinetic. Think of it as like shifting how much is on each of the bar graph. It's transforming. All right, I'll hit the stop button there. Go back to our video and hit to present mode again. All right, go through those big ideas. This is the big idea that we want to remember. Now let's connect that to the ski run example that you guys saw on the physics classroom. So I know lots of numbers, lots of different positions, lots of information on this graphic, but let's interpret it. Let's take it down in steps. So first off, when a skier has to get to the top of the hill, how do they get to the top of the hill? Well, they take a ski lift. The ski lift, you hop on the gondola or the chair lift, and that ski lift is going to do work to bring you to the top of the hill. So how much work is being done? Well, that work is going to be equal to that change in potential energy. We got 50,000 joules of work was done by the ski lift to lift you to the top of the hill. And that's how much total energy is now in my system. Okay. And that's important to remember because we're going to talk about the work for a roller coaster or ski lifts. All right. So now let's go to the next step. What is the total mechanical energy of the skier? And we kind of answered that already. It's equal to the work done to lift them there. It's also equal to the total sum of the kinetic and the potential. And if the skier isn't moving, then it's all the potential energy at the top. It's the sum of these two together. So that's going to be 50,000 joules. So what does that mean? That means as the skier starts taking his run and goes down and jumps and hits the ground again, the total energy, as long as there's no air resistance or friction or any kind of sound, which again is a very simplified case, that total energy is going to remain 50,000 joules. So let's look at different locations along the run. So here's the skier. He's picking up speed. He's going downhill. His height gets lower. So it goes from 100 meters to some lower height. Now let's say he's got 30 joules of potential energy. Well, where did that energy go? It was transformed into kinetic. And if I add these two together, look at the sum, 20 plus 30,000, 50,000 joules. My total energy is still the 50,000 joules. Let's take a look at another location. Now he's like nearly down right before the big jump he's going to take. His potential energy, his height is lower, lower, lower. So now my potential energy is lower. Now he's at 30 meters above the ground. Well, where did that potential energy go? It was transformed into kinetic energy. He's now going much faster here than he was up here. He's picking up speeds. And if you've ever done skiing, you know that you're going to be the fastest the lower you go. But we still see that the total amount, 35 plus 15, is still going to be equal to the 50,000 joules. Let's look at one more interesting spot right here. Now he's taking the jump, he's up in the air. So look at this. This dotted line right here shows what the skier's height is relative to the ground. Notice here he's got a height of 60 meters. He has the same height over here. How can I tell? Look at that potential energy. It's exactly the same, 30,000 joules, no matter what position he is. It doesn't matter if he's going downhill or jumping up in the air. That height is measured relative to the ground. So he's still going to have the same potential energy, which means he's going to have the same kinetic energy, which means, again, making connections, the skier is going to have the same speed, because kinetic energy indicates how much speed you have. It goes as the square of the speed. The same speed, whether he's going downhill on this portion, he'll have the same speed up in the air as he's like doing his big jump. So a lot of times students think, oh, he's got to be going faster here because he's going down. But it doesn't matter if he's going down or going up in the air. As long as the height relative to the lowest possible point is the same, it's going to have the same potential, which means he's going to have the same kinetic. So again, these two locations are going to be the same. And that's kind of an important conceptual thing that we're going to investigate with this roller coaster sim that we're going to do in a day or so. All right, so let's look at one more thing that I think is kind of interesting that we want to make connections about. We're going to see that this kinetic energy, what we started with, 50,000 joules of total mechanical energy, by the time I get to the bottom of the hill, I'm at zero height. I have zero potential energy. All of the energy has been transformed into 50,000 joules of energy, and it's all kinetic. So where is this skier going the fastest? At the very bottom, when all of the energy is transformed into kinetic energy. So this gives us a whole overview. We're going to be using these important points. We're going to reinforce it with a worksheet, and then we're going to do a lab. So, and the lab, again, is going to be a sim, except with a roller coaster. All right. Watch it again. If I went too fast, make sure you take it in steps. Good luck, everybody.